Hi everyone, welcome to this first recorded lecture of Randomized and Advanced Algorithms. So my name is Clément Cannon, I'm going to be the lecturer, and as you might see, this first lecture is not fully in person, but this is going to happen afterwards. So before starting explaining what the class is about, etc., I'd like to give you some administrivia, as usual. So the first step is the acknowledgement of country. So as I said, I'm not here with you, but I still would like to acknowledge the traditional owners of Australia and recognize their continuing connection to land, water, and culture. And I further acknowledge the traditional owners of the country on which you are and pay my respects to their elders, past, present, and future. All right. So the agenda for this first part of the lecture is going to be explaining what this is about. So what first, the arrangements for the unit, what expectations there are on your end and mine, what's the structure of the assessment, and a few, bookkeeping things about workplace health and safety, assistance, and advice. I'm going to go into more detail about that in the live version of this, so I'm going to go pretty quickly about the last ones, but at least I want to touch on the first parts. So, the lectures are Tuesday, 3-5 p.m. Except for the first two lectures, they will be in person, but the recordings are posted on to Canvas. The tutorials, check your timetable. There are two. It's of course in person as well. There is no recording, so if you're not attending the tutorials, you can decide to skip them. There is no mandatory attendance, but you will be missing out. It starts this week. There will be a first tutorial this week. And some things to keep in mind, basically go to the one you're assigned to. If you want to go to another one, you can, if there is room. If you cannot go to a lecture, please at least watch the recording. I'll go into a bit more detail about that, just to not be left behind. Now, in terms of people, well, the teaching staff is pretty small. It's only two of us. So I'm the lecturer and unit coordinator, Clément Cannon. This is my email address. As I'm gonna say again, you should not really use that on a daily basis. Everything will be through Ed. And the tutor is Joy Young. Now, in terms of resources, so we have a Canvas site. It should be pretty much up to date. You should know how to go on it, etc. There will be lecture videos that are posted there. That's where the weekly quizzes are going to be, but most of the rest is going to be on the Ed forum actually. So Canvas is not the main way I'm going to use to communicate with you. It's going to be on Ed. Discussion forums, that's where I'm going to be posting the slides, the tutorials, the tutorial solutions, the assignments instructions. That's where I'm going to answer your questions. That's where Joy is going to answer your questions. So essentially everything goes through Ed, and Canvas is just there as well. Another question is there a reference book? And like here, there's none. So you don't have to buy a book. You don't have to necessarily check a textbook on the library. There are some lecture notes that I'm writing and are posted on Ed. So basically a longer, more detailed version of the lectures with a lot more details. And of course, there are other resources. They are not mandatory. They're just for you to learn more things if you want. If you want to explore, go deeper, etc. And I'm happy to find more if you want. So again, if you're just thinking this is not in depth enough, or you would like to know a little bit more about something I've been talking about, just ask. I can find other resources. I can put them there for you. So please don't hesitate. Now, in terms of expectations, well, please attend the lectures if you can. Again, I'm going to go back to that in a little bit, but you also should work on your own. The lecture is not all there is, so you should be doing the assessments, you should be preparing for the classes, you should review for the classes, the usual, practice, self-assess. I want to trust you, basically, so you do what you feel you need to do in order to succeed. Participate in class constructively. So respect one another. If you know an answer and someone does not, be nice. That happens to absolutely everybody. Assume good intent. We all have the same goal, which is learning, succeeding in the class, and be enrolled if possible. Preferably it should be possible. Nobody knows everything. I don't know everything. I'm very happy to say I do not know everything. So keep that in mind. Now, in terms of checking ed, etc., please keep an eye on it. That's why I'm gonna post most of the announcements. So you should also receive emails about those announcements typically, but check ed. If you have questions, you can ask on ed. If you feel left behind, or like you're lagging, or like you're lost in the class, let us know. Again, we're here to help you. That's literally the description of our job, especially the description of my job. Now, the usual slide. Figure out by yourself. Ask yourself those questions. If you just remember what I just said, you should be able to answer them. If not, go back a few minutes past and listen to me again. I'm sorry about that. Now, two important things. Again, this is also in a longer form on the Ed forum. Please read those posts. But the first one is quite important. I'm not teaching this class to be adversarial. Like, the goal of this class is for you to learn things and enjoy that. So new ideas, possibly like challenge you a little bit in your learning. You should learn new knowledge, new skills. But all that is only possible if you feel good about it, if you feel included, if you feel valued. So my goal is to make that possible. So I want to create a learning environment where everybody, every single of you feels valued. You feel comfortable, you feel safe, regardless of race, ethnicity, religion, gender, sexual orientation, background, and so on. So I'm gonna do my best. I am fallible, we all make mistakes, but I'm gonna do my best. If anything is wrong, or anything can be improved, or you feel uncomfortable about anything, reach out to me. Again, I am very open to feedback. I want to make this class good for all of you. And you can give me anonymous feedback as well if you feel uncomfortable. So that's the first important message about just the class in general. The other one is, well, as I said, it's a challenging course. It's been designed, it's in the title, right? Randomized and advanced algorithms. It's been designed to introduce things you haven't seen before. So there's a good chance that's going to be stressful. That's not the goal. That's an unfortunate side effect. I want you to succeed. I'm not your adversary. I want you to have fun while you learn. If I teach this unit, it's because I think what I'm trying to convey is interesting. I like those algorithms. I like all those things, and I hope to be able to make you like it as well. So if anything feels unsurmountable, please ask questions. Reach out to me on Ed. That's one of the few occasions where I encourage you to use emails as well if you want. If you start, or in person. If you start feeling left behind in class, let me know. And okay, the last one, I don't want to sound patronizing. This is just a friendly advice. Try to maintain a good work-life balance. It's very easy to get sucked into like some spiral of stress, bad habits, feel terrible, don't sleep enough. Please try not to. I'm not just saying that because it's nice to feel good, but also that also will help you learn, even if you don't realize it. So try to maintain that work-life balance. This is a course, and this is just a course. Right? This is not the most important thing on earth. All right, so a bit less fun or more fun, depending on how you look at it, the assessment. So of course, this being a unit at the University of Sydney, there will be an assessment of what you've learned and your performance. Again, hopefully that should not be too bad. I noticed already a typo in my slide, so it's roughly every 4 weeks. It's written with a programming component, each assignment. Altogether, there are 45% of the final mark, and they're equally weighted, so 15, 15, 15. There also are quizzes, so we have basically one quiz a week from the end of one class to the next class, unlimited time to answer. It's 9% of the final mark. And how is it gonna work? Well, you do 12 quizzes, I pick the best 9 out of them, and each of them is 1% of your final mark. There's also that weird thing that I call participation, and the idea is I'm gonna give you during the semester like several possible problems, like exercises, either in the lecture notes or separately, and that's going to constitute a list that's going to be available to everybody. All you need to get those 6% is like pick one problem, any problem you want, solve it, and submit it to me before October 18. And I will mark it, of course. It needs to be correct, your solution. It should not be too challenging, but you have a lot of time. Just pick the one you want, the one you feel the happiest about. You solve it and you send it to me before the end. You submit it to me before the end. So if I haven't messed up the counting at this point, that should be 60%. The 40% remaining are the final exam. So it's going to be in-person supervised at the end of the semester, and as is standard in the School of Computer Science, you need to get at least 40% of those 30% to pass the class. If you pass the threshold, then the mark you get accumulates, and your final grade is the sum of all those things. Hopefully that's clear. If there's any questions, again, please ask on it. Now, okay, this is the one I kept referring to, lecture attendance. So lectures are not mandatory. They are definitely encouraged, but I know each of us is different. We all might learn in different ways. Some of us don't like to learn live. Some of us prefer textbooks. Some might live very far and not enjoy a 2-hour commute for one lecture a day. It's definitely up to you. You do you. Lectures are recorded. You will be able to watch them afterwards. I personally prefer not to be alone in the classroom. I know this is a bit ironic because this one is actually remote, but it's going to be in person starting lecture 3. And I encourage you to be here if you can. It's a bit lonely if I'm the only one in the lecture hall. But I mean, regardless, do watch the recordings, please. Whether you watch them live or you watch afterwards, please watch the lecture in one way or another. And as an incentive, what I will do is like every lecture or other lecture, so starting maybe at like lecture 2, I'll take a few minutes sometime during the lecture to just solve some question from the current assignment. So I'm not going to say when, I'm not going to say what, but there's going to be like a few basically like freebies hidden in the lectures. And again, if you watch the recording, you will find them as well. But that's just a small incentive to watch the lectures. Oh, and to conclude also, the tutorials are not recorded. They're not mandatory, but they're definitely part of the class. So try to attend as much as you can. Now, here are the deadlines for the free assignments. Again, if they feel difficult, please ask questions on it. Of course, we won't give you solutions, but we are happy to try to discuss some points. If you think something is confusing or if you're lost somewhere, we can try to help you without giving you the solutions as well. I will stop here with this administrivia part. There is more. I'm going to go through that in the live lecture tomorrow. But special considerations, late submissions, academic integrity, and basically all the things that is not very fun to listen to, but you definitely need to know. So again, we're going to get back to that. All right. So now I'm going to switch to the other part of the lecture. So now we're going to go into the actual content of the lecture. So lecture 1 is going to be about randomness, probability, and algorithms. I'm going to start with a small experiment. You shuffle a deck of cards, so 52 cards. You shuffle it well so that it's actually uniformly random, the permutation. And then you look at them one by one, starting with the first card, then the second, etc. And you count how many times do 2 consecutive cards have the same suit. So for example, by suit I mean heart, heart, or like spade, spade, that kind of things. So here's a very fun aspect. I did, this is actually a random shuffling of the 52 cards. And then, I go by order. So 4 of hearts is followed by 3 of hearts, or that count as like 1 time 2 consecutive cards, so I'm at 1. Then 8 of clubs 2 of clubs, oh, another one, 2 times, then like 3 of spades, well, clubs it's spades, so not consecutive, then 10 of heart, then diamond, then I've got spades, heart, diamond, heart, heart, another one, then club, club, another one, spade, heart, spade, spade, another one, etc. And I keep continuing. So here, for example, you might notice I've got like spade, 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 spade. That counts as many consecutive, right? That counts as like 3 consecutive things. I've got like the queen, then the 2, then I've got the 2, then the 10, and then I've got the 10, then the 6. Anyways, so I count all that, and again, how many times do 2 consecutive cards have the same suit? In expectation, right? Because I just shuffle once, that gives me a number, I can't infer anything of that. But if I keep repeating that, I might be like, oh, actually, like most of the time, or like, not most of the time, but maybe on expectation, the average looks like it's some number. What is that number? I'm not asking you to necessarily know or figure it out right now, but hopefully at least the question makes sense. And given such a question, you have 2 options. Either you know exactly what to do, you start writing down equations and like you figure out the answer, or another way is to try, right? Like to try to get a feel of the answer before trying to prove it. So of course, I'm not gonna do that right now. I'm not gonna like take a deck of cards and like spend the next hour and a half just shuffling cards. But nowadays we can actually do things a little bit faster, so we can write some code. I'm not saying I'm a good coder, but like I can do this. So, you know, we run an experiment, a simulation. We can actually get some empirical numbers pretty fast. So I actually did it for you. This is what the numbers are. So like, you know, I made many experiments, 500 I think. And like sometimes I only have like 5 times, but that's pretty rare. Most of the time, like it's, you know, it looks like most of the time it's around 10 and 15, and actually like that red dashed line is the average. And well, okay, it's maybe not that apparent on this slide right now, but like it's pretty close to 12. Looks like, you know, maybe like 1159 or 1201, but like something very, very close. So that at least tells us that it should be something around 12, and if we believe that like round numbers are nice, so with 52 cards, let's try we do that. Maybe we can try to prove that it's 12. That'd be nice. Can we prove it? Hopefully the answer is yes, but how do we prove it efficiently? So one thing that in this class is I'm gonna try to give you some techniques to prove things about algorithms. It might not look like it, but right now, like this is very related, like general techniques. And since we're looking at an expectation, this technique will be about like expectation of random variables. So again, I assume you have seen the symbol for expectation. You've seen like some basics of discrete probability before taking this class. If not, again, ask me on Ed. I can point you to things and I can try to like help. But the first thing that we're going to use is linearity of expectation. This is one of those things that seems very, very basic, completely non-impressive. You know, you see that, you're just okay. But it's incredibly powerful when you use it. So what does it say? A linearity of expectation. It just says that if I have 2 random variables x and y, such that they each have an expectation, right? Expectation of x should be well defined, not infinite, well defined, and expectation of y as well. Well, the expectation of x plus y is the expectation of x plus the expectation of y. And again, that doesn't seem very impressive. The key thing here is like it works even if x and y are dependent in like arbitrary weird ways. It makes no assumption at all about the relation between x and y. It just says like no matter what x and y are, as long as expectation of x exists and expectation of y exists, then the expectation of the sum is the sum of the expectation. And that's very useful. How useful? Well, we're going to see. And you're going to see more in the tutorials. But let's try to see this like this. So let's see if I can do that live. Yes. So how many times do 2 consecutive cards have the same suit in expectation? Okay, so we've got those cards, right? So like, we've got, I shuffle them, and I've got a lot of them, so 52 in order. And what I can do is like, well, if is this one, this is this pair sharing the same suit, is this pair sharing the same suit, is this pair sharing the same suit, etc. So how many of those badly drawn circles do I have? Well, 51. It goes from 1 to 51 because it's 1, 2, 2, 3, etc. and then 51, 52. So let's just say that I'm gonna call something for like I between 1 and 51. I'm gonna say that and I'm gonna call that yi is equal to 1 if card I plus 1, again after the shuffling, share a suit. So again, by a suit I mean like heart, spade, etc. and 0 otherwise. And then what I'm interested in, pretty much by definition, is the sum of those things, right? The sum of those things literally tells me how many of those pairs share a suit, and I'm interested in like how many of those pairs do share a suit. So again, if the first card is a spade and the second card is a spade, then x1 is equal to 1. If the first card is a spade and the second is a heart, then x1 is equal to 0, etc. If x1 is equal to a heart and x2 is equal to a heart, then x1 is equal to 1. So I'm interested in this thing. And what can I say about each individual yi? Well, what is the expectation of yi? The expectation of yi for any I, it's the probability that card I and I plus 1 share a suit. Okay, so let's think about that. Card I, so fix I, card I has some suit. It's either heart, spade, club, or diamond, right? It's one of those. So whatever it is, let's call that like S. Card I has some suit, it's S. What is the probability that card I plus 1, ignoring every other card, what is the probability that card I plus 1 is also suit S? Well, I just told you that like card I is S, so how many other cards with the same suit are there left? Well, I've got 52 cards. There are like 13 spades, 13 hearts, 13 diamonds, and 13 clubs. So I've got one in my hands, it's the ith card. So I've got 12 left. Okay? 12 out of how many? Well, again, I've got one card in my hand. So how many more do I have? 52 minus 1, 51. So the probability that this probability is, as I said, 12 divided by 51. And you can see it as like 13 minus 1 divided by 52 minus 1. Okay, so we have the expectation of, so what we just said is expectation of y1 is expectation of y2, etc. is expectation of y51 is equal to 12 over 51. Okay, but that's not what I'm interested in, right? I'm interested in like expectation of y. This is the thing we want to figure out. And expectation of y, since the way we define the yi's is exactly the expectation of sum of I is equal to 1 to 51 of yi. And that's the part that seems annoying, right? Because these things are definitely not independent. y1 is definitely not independent from y2. They share a card, right? y1 depends on card 1 and 2, and y2 depends on card 2 and 3, and so on. So you have a lot of dependencies in there. But linearity of expectation does not care about those dependencies. So by linearity of expectation, I can just take the sum outside. Sum of expectation is equal to expectation of the sum. Oh, that's not too bad, right? Because that thing is exactly what we just calculated. So that's sum from I is equal to 1 to 51 of the same number, 12 over 51, which is equal to, well, 51 times the same number. So here we go, that thing cancels, and this is exactly 12. So again, linearity of expectation here allowed us to just completely ignore the dependency. So we define the right random variable. Here this is 1 if card I has the same truth as card I plus 1, 0 otherwise. We expressed the quantity we're interested in as the sum of those things. They're very dependent, but we don't care, because the expectation of the sum is the sum of the expectation. So all we needed to do is figure out like the expectation of like each of these much simpler things. We did that, that was 12 over 51, and then we just sum them. So hopefully that was illustrative of what we can do with linearity of expectation. Again, you're going to see a lot more in the tutorial. With this in mind now, let's go back to randomized algorithms, because it's nice to shuffle cards, but there's a little bit more in this class than that. So again, you've taken some classes on algorithms before, and I'm sure someone has made that comparison to you. An algorithm is a recipe. I give you an input, the algorithm is a bunch of steps, that gives you the output. So you put ingredients, you get cake. The beauty of deterministic algorithms is like, if you give the same ingredient, you get the same cake. You repeat, you get the same cake. It's deterministic. Randomized algorithms are a bit like cooking with kind of weird equipment. You cook with randomness. Your recipe has like a non-deterministic aspect to it. So let's just think, for example, your oven is a bit unpredictable, a bit magic. So given some input, you follow the steps, you get, I don't know what that cake is. I'm gonna say like strawberry cake. You put in the same ingredients, you follow the same steps, somehow you get a birthday cake. So, I mean, I'm gonna try to be a little bit more formal than that, maybe. So randomized algorithms are algorithms where the behavior does not just depend on the input. It also depends, at least in part, on some random choices. Think of that as like tossing a coin repeatedly, or like tossing a die and like giving that to the algorithm as well. So think of that basically as an algorithm that's allowed to toss some coins to get some random bits. There are some important distinctions I want to make. What is and isn't a randomized algorithm? So here, like, we're not assuming the input is random. In some cases, applications we might, but this is not part of the definition of a randomized algorithm. The input is just the input. Like, I give you a graph. That graph has nothing weird about it. It's a graph. It's fixed. I give you an array of n numbers. Those numbers are not like weird random things. It's an array. It has numbers in it. And typically, we're going to take the worst case of all possible arrays as usual. We don't also assume, like a lot of times people think of random as like kind of average. We are not just saying like, oh, it's the same input and like we just call the algorithm many times and we take the average. This is not this. That has another name. That's called average time complexity. It's different. This is not what we do. Here, the input is worst case. So I'm going to look at the worst possible graph for my algorithm. Or I'm going to look at the worst possible sequence of n numbers, but the algorithm gets to make some random choices. And sometimes that helps. We'll see some examples. So maybe a way to look at it is what you've seen before. So an algorithm is just a nice black box. So that's my algorithm A. And I give it an input X, and it does some stuff. It usually does some stuff. And then it outputs some value A of X. So that's deterministic algorithm. Randomized, well, it's a bit different. Same thing. So you've got your box A. It gets some input X. But what it's also going to do is like, it gets some like randomness. So it tosses a coin, or like it gets, I like to think of it as like it gets a sequence of like random bits. And think of that as like there's some random bits it observes in the sky, and that it gets that. So let's call that R. And the algorithm will output something, but now think of the input as being both, like there's the input X and there's that random string R. And that's randomized. So if you think of it that way, what we're actually looking at is, over a random choice of R, what is the output? So again, this is worst case, this is the input, and this is just random. So that's, I would say, the right way to think of a randomized algorithm. It gets an input and it has access to some like random tape that it can look at as well and use that. And if you call on the same input X, the random tape might have changed. All right. Now, that being said, again, there are several distinctions about randomized algorithms. So you could have some, we're going to see some examples of both of those. So, you know, since the algorithm A has access to some random bits, the time it takes to process the same input X, you know, could depend on like the random bits it got. So the time T that the algorithm A spends on X, it also depends on R. So the time itself is random. And so, you know, maybe the algorithm has a random running time that depends on R even for the same X. It could also output something that changes with the random bits. So what can be random? The time it takes on a given input. So fix X. Random because this thing is random. Or like the output could be random. So an example of the first one is randomized quicksort. We're going to see it again later in this lecture. What it's going to do is, well, it's a sorting algorithm. You give it an array of n numbers. It will give you a sorted array of n numbers. It will sort the array no matter what. But the time it will take is not always the same, because it's going to make some random choices, and sometimes it's going to be really fast on the same input. It could be fast or slow. So on expectation, it will run in some time blah, but the time it takes on the same input will depend on the randomness. So, but always give a correct output. So we call that a Las Vegas algorithm. Las Vegas, always correct output. The time is random. We will give like bounded in expectation. And the other type is Monte Carlo. There are more, but the main two types are Monte Carlo. And Monte Carlo, you just swap the two things. Sometimes incorrect, with small probability. You know, so you still want most of the time the output will be correct, but with small probability over the choice of the random bits, it might output something wrong. But time always bounded. Even in the worst case of all the random bits, etc. So those are the two main tips we're gonna often go to. But it's more general than that, right? You could also have something that even if the algorithm is always correct, the output might not always be the same. So an example is, for example, like find something in a graph that has a good that has like nice properties, like find a vertex that has at least 5 neighbors. If you start by like picking a starting vertex at random and then like exploring, doing a BFS from that vertex until you find some vertex that has at least 5 neighbors, you might just output a different or like output like abort if there is no such vertex in the graph. You might not always output the same vertex. There might be many vertices that have more than 5 neighbors, and depending on where you start, you might pick a different one. So your output is always correct, but it's not necessarily always the same output. So, you know, there are like many ways one can quantify that, but really like usually the main 2 distinct things we're looking at is Las Vegas. It's always correct, but all I can say is on expectation, it is fast. Or Monte Carlo, which is like, it's always fast, but it's correct most of the time. And in case you're wondering, those are actually the names of 2 casinos. I don't remember the history, but there's a reason behind that. All right. Okay, maybe now it's time to ask the question, why do we want to look at randomized algorithms? I mean, we have perfectly good deterministic algorithms, right? Why do we bother? One of them is to avoid pathological corner cases. Sometimes it's just the case that your deterministic algorithms are slower than they should, or like they're really annoying, or like they fail, but for like a silly reason. It's just like, yeah, there's like one possible corner case and they get stuck at it, but like if only I was to consider that only with very, very small probability, then I would be fine. So you can try to use randomness to like get you out of those like corner cases. Another version is to get approximate results, but very, very fast. You know, I don't really care about like the exact number, or I don't actually care about getting the exact result. I want something that's good enough, but I'd like to do that very fast. Well, randomized algorithms are great for that. You start like, you can do like random exploration, random things really, really fast, and typically that will allow you to get like a pretty good idea of the result in some cases without having to like know the result exactly. That also allows you to avoid predictable outcomes. Sometimes that is really useful for some like critical applications. You do not want someone to be able to predict what the output is going to be, or like to look back at what the input should have been given the output. So adding some randomness allows you to avoid that kind of things. One example that is the last line here is privacy. If you want to preserve privacy of a dataset, you might want to add some uncertainty about it in the output. And what's the best way to add uncertainty to something? Randomization. The thing we're going to usually focus on in this class is to get faster, simpler algorithms. You know, even if you have a very, very efficient algorithm, or just like an algorithm that works and is deterministic, sometimes just a randomized algorithm is just going to be much faster, much simpler to implement, much simpler to look at, much simpler to analyze. And finally, 2 other things, like to break ties or bypass impossibility results. So break ties, for example, you know, if I tell you like, oh, we have to assume that all numbers are distinct, otherwise like, it's annoying to handle, etc. Well, you can break ties. You can just like toss a coin, and if 2 things are equal, you say like, I'm gonna output the first one if it's tails, the second one if it's heads. That's good. That is usually useful, and we're gonna see things like that in the following lectures. In particular with like the power of 2 choices, that is like the best way to break ties and get an ultra efficient algorithm just by that idea. The last one is like cryptography and privacy. As I mentioned, there are things for which you actually need randomness. Without randomness, things are actually impossible. And those critical applications, just by themselves, they should motivate that. But now, there's a lot to say in favor of randomized algorithms. Again, that's basically what I do for a living, so I'm pretty biased. But there are also things to say against it. Why not randomization? And one aspect is like randomness is not always good or desirable. You know, even if like some people do not want a randomized output. If I tell you that like you're not gonna get your bank loan, and if you ask me why, you say like, well, I tossed a coin, and like the algorithm, like based on that coin, said no, you're not gonna be very happy with this outcome. So it sometimes hurts interpretability, or like hurts to have algorithms that are randomized in that way. This is a very valid point. Another one is actually just random bits. I mean, we assume there's that magic random string in the sky, or like you can toss coins and get randomness. In practice, random bits, you have to generate them. They don't grow on trees. And it's really hard to get good randomness, because if you assume that this is a bit, it's 0 or 1 with equal probability, and it's very useful, it's really hard to generate those things. And like especially to generate a lot of them, and they must be independent, and they must be like, not predictable, and so on. It's really hard to get. And if you've got bad randomness and you feed that to your algorithm, you might get bad outputs. You might get like something really bad. There are like a lot of stories about people running algorithms with very poor randomness, or like poor, pseudo randomness, something that replaces randomness when you don't have actual randomness. And since those things were like definitely far from random, the output of the algorithm was like pretty much garbage, which could be an issue as well. And just to conclude this part, I just want to mention that, for example, if you've ever used np.random in numpy.random in Python, this is approximately random. This is not like good quality randomness. It's good enough, and we're going to use it in this class for examples. That's what I'm using for that. But if you're ever doing something that requires like actual randomness, think again of cryptography or privacy or anything where like you need to make sure that your algorithm behaves like it should be if the things were actually random, do not use that. Use, for example, secrets instead. It's a secure pseudo-random generator, PRNG, which replaces randomness. But do not use np-random if really it's crucial that the things you're using is actually random. That was just a small PSA. It's actually pretty important. And again, if you want to know more about that, feel free to ask me. All right, so we're at this point where I made a very abstract case about why do we want to use randomization. I haven't given like anything more than generalities. Hopefully you believe me, but here's an example. Very simple. I give you a number. It's a big number. It has n bits, or even n digits, let's say. So I give you an n bit integer. It's huge. N is huge. It's like a very, very big number. And I ask you, is it prime? Now, okay, maybe you don't care about that kind of stuff, but it's actually very, very useful for pretty much all of cryptography at this point. So generating checking if a number is prime is like really important. So I've got good news. There exists a polynomial time algorithm for that. I've got bad news. It's a pretty recent algorithm. That was actually 2002. That was a huge open problem. People have been looking at that for a long time. So it's only like 20 years ago. And it's non-trivial. Like that algorithm is non-trivial. Also, it's very slow. The running time at the time was like tilde of n to the 12. If you don't know what the tilde means, don't worry about that. Like n to the 12. It's n to the 12. The tilde actually means like n to the 12 times like some logarithms in n as well on top of it. But like n to the 12. This is not a good polynomial. This is very slow. That was only the beginning. Then like a lot of work has been put in, and it's been improved quite a lot. Now it's n to the 6. I think that's the best known for this algorithm. So again, it was not known whether it was doable in polynomial time. Turns out, oh great, it's possible with a deterministic algorithm in polynomial time. That's like, yeah, and that polynomial is n to the 6. And again, it was non-trivial, right? That was the first one that did that. The authors like AKS were celebrated for that, and like got like 2 of the most prestigious prizes in theoretical computer science for that. The Gödel Prize and the Fulkerson Prize for this. It's a big deal. But n to the 6. On the other hand, there's a very simple randomized algorithm. It's known since 1980. There was a version by Miller in 77, and then Rabin made it actual faster and using randomization, and it's been known for like 20 more years, and it runs in times n squared. So, and it's simpler. It's much simpler. So, you could use the n to the 6 deterministic algorithm, or like you could use the n square algorithm that is only correct with probability like 0.99999999%. 99.99999%. And if you're not happy with that probability, you can just repeat it a few times, and like that 0.00001% of failure like decreases really fast. So again, either you spend n to the 6 time using the deterministic algorithm, or like you spend roughly n squared, and like your probability of failure is smaller than the probability your laptop just explodes by itself. That should make a pretty compelling case. So yeah, primality testing, good example of where you want a randomized algorithm. Now, let's actually analyze a randomized algorithm, one that you probably have seen before. So first, just so we're on the same page, sorting algorithms. I give you an array A of n distinct numbers. It doesn't need to be distinct, but I'm just doing that for simplicity here. And your goal is to sort A. So the good news is, as you've seen in previous classes on algorithms, there are deterministic sorting algorithms with running times big O of n log n. And they're comparison based, which means basically all they do is like compare numbers. They don't like look at the value of the numbers or whatever. Also, I have like even better news is like you can do better. Every comparison based sorting algorithm, it's a bit annoying to say comparison based, but it's necessary. So every such sorting algorithm must have worst case running time omega of n log n. So we have some deterministic algorithms that have worst case running time n log n, and all of those algorithms, for all of them, you can't do better. So that's pretty good news. And you know some of those algorithms that achieve that. So heap sort, merge sort, there are several of them. So now quicksort. Quicksort is this algorithm. How does it work? It's pretty nice. It's pretty simple. So you've got your array of n things, and like you pick a pivot. That's the magical part. How do you pick a pivot? So let's just say like you pick a pivot. Like let's say this is the pivot, and then like you partition A into 3 subarrays. So since I assumed all elements were distinct, I only have 2 subarrays. So I'm gonna look at like the elements that are like, so if that's my pivot P, I look at the elements that are like smaller than P. So there's gonna be like this one, this one, this one, this one, maybe those ones, and maybe this one. Okay, cool. And I look at the elements that are like greater than P. So maybe that's for simplicity. Let's not do that. So maybe this one, this one, this one, this one, this one. I mean, those that remain, right? So I've got, I've got like 2 subarrays, smaller than P, elements that are smaller than my pivot and elements that are greater than my pivot. And, I look at them separately. I know where they should be compared to P. So like, now like P is still here, let's say. And then I've got all the ones that are greater, I'm going to put them on that side. And all the elements that were smaller, I'm going to put them on that side. Those 2 things are not sorted. So that's A1, and that's what I call A3. And again, like, since I assumed all elements were distinct, A2 is just P. But now I can just recurse, right? I can just recurse on A1 to sort that part. I can recurse on A3 to sort that other part. And recursively, I'm gonna sort those things, and after that, the whole thing is gonna be sorted. So that's quicksort. The only kind of magic part is like, how do I select that pivot P? Because clearly that matters a little bit. If I select P badly, A1 is gonna be very small, and A3 is gonna be pretty much all of A, and then like recursing does not actually bring me that much. So the bad news is quicksort is actually not an optimal in the worst case algorithm. Worst case, it's, well, if you're unlucky, your choice of pivot, which you do deterministically, right, because you're the deterministic algorithm, is going to be pretty bad. And so as a result, your running time is going to be n squared. At least if you pick like something simple, like I'm going to pick the pivot naively, which most of implementations do, then this is worst case n squared. People still use it because, you know, the worst case is just the worst case, but like most of the time it's going to be really fine. And it's a nice, simple, easy to implement algorithm. So people use Quicksort, even though technically its worst case is n squared. I have to say one thing though, about this is like there is a way to make Quicksort run in times big of n log n in the worst case by using something very, very, very like smart to choose the pivot. So you choose the pivot as like the approximate median of the array, and like, oh, but can I find the approximate median of the array fast enough? And oh, it turns out you can do that in linear time, and that's great. The issue is like you can do that, so can make big O of n log n by using very smart, it's better if I know how to write, very smart pivot strategy. So that sounds good, but the issue is like, it's not simple, it's not nice, and you know, it's not that fast in practice. I mean, you lose constant factors. So like, if you do that, you completely annihilate that last sentence. Because finding the median in the approximate median in linear time is, it's an exercise. It's not a simple algorithm. So again, for all matters and purposes, all implementations of Quicksort use a simple pivot choice strategy, and that means that in the worst case, that will be n squared. But in practice, that kind of goes fast. Anyways, again, the choice of pivot is like the magic of Quicksort. That's the only part that like you get to toy around when you implement Quicksort. So this is a randomized algorithms class. We want to look at a randomized Quicksort. So let's just say like, how do we select this? Like select at random. Let's just pick a random pivot, right? Like we have n possibilities for the pivot because it's an array of n numbers. You can choose any of those n numbers to be the pivot. Let's just pick uniformly at random. Oh, this is gonna be like element at position 17. Let's go. Does that work well? Well, I mean, this is a very natural thing to do, at least, so we have that for us. There is the advantage of simplicity. And lo and behold, this is actually a very good thing to do. So if you do that, randomized quicksort is a sorting algorithm with expected running time n log n. And again, as I said, this is a Las Vegas algorithm. The running time is expected n log n. In the worst case, that's still going to be n squared in the worst case. But by worst case, I mean worst case over all possible choice of the random bits. But that happens with, yeah, we don't really care that much. The expected k, the running time is n log n, and it always outputs a sorted array. And it's still nice, it's still simple, and it still does well in practice. So pretty much like all we could want. All the advantages of quicksort, but on top of that, expected running time, we can analyze it. And I hope we can, because that's what we're gonna do now. So again, randomized quicksort, we choose the pivot, and then we have to handle that. So how do we do this? Well, we're gonna try to bound the expected running time. So I'm just gonna say t of n is equal to expected runtime of randomized quicksort on array of size n. Again, when I say expected running time, it's going to be like for the worst possible input array of size n, but after expectation over the randomness of the algorithm. And if we look at what the algorithm does, again, think of it as like you've got your array. Now you pick a pivot uniformly at random. So like, oh, this is my pivot, p, and then you put all the elements smaller than p on one end, maybe that's a bad, let me do that differently because this is a bit misleading. So this is P, and let's say P, like only those elements were bigger than P. So not a lot. Well, this is my new array, and then like this is gonna be A1 and this is gonna be A3 greater than P. So what we can say is T of n, I start with an array of size n, is equal to, well, I'm gonna have that as like expectation of T of A1, that's the size of A1, plus expectation of T on an array of size A2, because I give it A2, plus, as usual, the big O of n, because, you know, doing this thing takes big O of n time. And why am I putting expectations here and here? Because that's weird, I just said that I was taking Tn to already be the expectation. It's because here the expectation is over the size A1 and A2. So expectation over A1. Because, you know, the randomness of the algorithm at these particular steps will make it that, like, if I had picked another pivot, A1 could have been smaller or bigger. All I know is A1, like the size of A1 plus the size of A2 is like n minus 1, because all elements are assumed distinct and I don't recurse on the pivot. But the balance of the balance between the two depends on the pivot, and the pivot is random. So that's what I have here. So now I want to solve this expectation, this equation. How do I do that? Well, let's just say that what I can do is write down this expectation. I can, right? I can just say that expectation over A1, what does that mean? Well, that expectation depends on the choice of the pivot. That sounds good to me. Since I picked the pivot as at random, what is the probability that the pivot is, probability that P is the kth largest element of A? Well, I mean, it's 1 over n, right? It could be the first element of the first biggest, the second biggest, etc. But like they all have the same probability because each of like the kth element is just one element of the array. I pick this element with like probability 1 over n. The k plus 17 elements, biggest element of the array, is another element, and it could have been picked as well, but with the same probability 1 over n, because I choose the pivot at random. So this is always 1 over n for all k. Which is good because, again, if I pick the pivot to be the kth element of the array, what does that mean? That means like the size of A1 is k minus 1, because it's all the elements that are smaller than P, than my pivot P. Then the size of F3 is n minus k, because I've got k minus 1 elements that are smaller than P, I've got P, and then I've got everything that remains that will be bigger than P. So I can rewrite this as, I'm going to put the big O of n first, plus sum from k is equal to 1 to n, all the options, times t of k minus 1. This is what happens is if p is the kth biggest element of A, plus t of n minus k. This is what happens for A2 when p is the k biggest elements, times the probability that p is kth largest. And we just saw that this thing was 1 over n. So I get t of n is equal to big O of n plus 1 over n sum from k is equal to 1 to n of t of k minus 1 plus t of n minus k. Okay, that's, I guess, nice. What do we do with that? It's kind of annoying, but we can rewrite that. You know, we can break that sum. It's like the sum from k is equal to 1 to n of t of k minus 1 plus the sum from k is equal to 1 to n of t of n minus k. And then if you break the two sums and like you set L is equal to n minus k and you like make that changes that you will actually get like with twice the sum. So you can just, I'm happy to elaborate on this live, but you can just write that as like it's equal to the same thing, but now I've got like L is equal to 0 to n minus 1 of t of L. Again, you separate the two terms to get two sums, and then like you change, you said in one you said L is equal to k minus 1, and the other one you said L is equal to n minus k, and you see what happens, and you're gonna end up with twice the same sum, and that gives you this thing. Okay, again, I'm not sure exactly what we want to do of that, but this is what we get. So now what we are left with is this beautiful recurrence relation. So I'm just going to replace the big O by C times N. That will help with the recurrence relation, but that's what the big O is anyway. It's at most C times N for some C times L is equal to 0 to n minus 1 to T of L. And that's the part where like I say, oh, this can be solved. So how do we solve this? There are several ways. One of them is just to be like, we wanted to show that it was n log n, so like let's just prove by substitution that n log n works, and then we're good. That's one way. You can prove it by induction, basically. So this is in the lecture notes. The other way, which I'm gonna give because I find it more instructive, and that's also another technique that is quite general, is we have something very discrete here, right? Like we assume like it's a function t of n. N is an integer. We want to solve that recurrence relation, but we don't know. And let's say I hadn't told you the answer was n log n. How are you gonna figure it out? You're gonna try, like, you need to build intuition about what the answer is before trying to prove it. A good rule of thumb is, well, under some very mild assumptions, which is basically like whatever we're trying to do, like t is well behaved, it's increasing, like it's nice. It's a running time. It should be increasing in n, for example. Then we can just basically like forget this is integers and just say like, let's look at the continuous counterpart. And you know, if you've taken real analysis or if you're more comfortable with like derivation and that kind of stuff, that can be very useful. So let's just say we want to replace t of n by some function. So let's just say up, we're gonna replace that. That's a terrible sign I just used, so let's just replace that with everything. Let's just say like, okay, what if we replace t of n by f of x, some continuous function? And what does that become? And well, if we do that, then it doesn't make sense to have sums, so like sums become integrals. And n becomes x. And again, this is a rule of thumb, but like this can be made quantitative. So let's do that. With that substitution, what we want to solve now is f of x is equal to c of x plus 2 over x integral from 0. N minus 1 doesn't really make sense, right? Like it's continuous now, like between n and n minus 1 we're like doing an integral, so it's just like it's x, and f of u du. That's what we want to solve. Okay, it doesn't look like this is much better, but now we have like hundreds of years of people studying calculus that can help us. You can plug that in Wolfram Alpha at least to have a sense of what the solution is. I'm just gonna give you like quickly a way to look at it. So let's just call that big F of x, you know, it's the integral. And like what we get is f prime of x is equal to c of x plus 2 over x f of x. Oh, that's a partial, like that's a differential equation. What do we do with this? We hope for the best, I guess. But like once you know what to do, you can just do f prime of x divided by x squared. So you divide everywhere by x squared is equal to c of x plus 2 over x cubed, because that's what shows up here. Why are we doing that? Well, this putting things together, that's like f of x divided by x squared minus 2 over x cubed. That's a cube. F of x is equal to c over x. Okay, but no, that's nice. Here, like magically, or like ask Wolfram alpha again, you can recognize that this is the derivative of d over dx of f of x, almost there, over x squared. So you can basically integrate both sides and you will get like f of x over x squared. So with that you integrate is equal to, the other side is nice to integrate because the integral of 1 over x is log x, c log, so c log n, I'm just gonna write log, c log x plus like some constant, whatever that constant should be, k. And at this point, you basically have found f of x. F of x is x squared log x plus k x squared. And we're almost there because what was big f of x? Well, it was the integral of little f of x. So now all you need to do is differentiate. And you get f of x. Don't worry if you're not like following that much. This is just a rule of thumb. Like those last steps can be automatized. I'm just telling you, like, I just want to get to the result to show that this works. So f of x is, so if you differentiate, you will get like basically cx log x plus some negligible stuff. So we get cx log x. That tells us that little f of x is cx log x, or little f of x corresponds to t of n, so t of n should be c times n log n. Once you know that, then like either you make this kind of like correspondence between continuous and discrete formal, or you're just like, oh, now I know what I need to prove, let's do it by induction. Or if you're really like, I should not encourage you to do that, you can just say like, it is obvious that the solution to this equation is this. Please don't do that in your homework. But yeah, anyways, now we have that recurrence relation, we can solve it, that gives us the right thing for Tn, and we're done. So that was the end for this lecture, almost. Just a small recap to look forward. First of all, what did we see? Well, what is a randomized algorithm? Why would we want randomized algorithms? Why would we not want randomized algorithms? Are they actually that useful? We had like at least one example, prime numbers, and then like randomized quicksort. Are they actually easy to analyze? Well, I hope I didn't scare you with like that last part where I solved the recurrence relation, because all the work is to get to that recurrence relation, and after that, your job is done. This is just solving some like kind of math puzzle. But yeah, so we can prove quite easily, quite a lot, just with linearity of expectation. Like this is essentially what we use also for randomized quicksort. With an expectation of two things, we split in two and so on. So next week, we're going to go beyond linearity of expectation. We're going to see something called concentration bounds and probability amplification. Concentration bounds is basically saying like, oh, it's really nice to have something about the expected running time, or it's really nice to have something about like the expected quality of the result. But like, what if I wanted something that's actually just like most of the time with probability 99%? Can I, with probability like 0.999 and like 99.999? What do I pay to convert from to go beyond just expectation? And there are ways to go there. That's called concentration bound. It's to see like how well things concentrate around their expectation, essentially. Probability amplification is just saying like, well, I give you something that is kind of nice, but succeeds with probability 51%. Can you make it succeed with probability 99%? And again, the answer is yes. And another version is the median trick. So we're going to see all that, part in the lecture, part in the tutorials next week. After that, we're going to go towards like a lot of cool names like coupon collector, load balancing, power of two choices. Those things are actually like deep techniques that will get you a very long way in analyzing algorithms. They basically think of that as like abstracted version of some problems you might want to solve and appear everywhere, and like we're gonna solve them. So that de-randomization is just like, oh, I have a randomized algorithm. Can I make it deterministic now? I mean, I did the nice thing where like I get a simple algorithm. Can I make it like deterministic just by staring at it? Sometimes you can. That's nice. Then we're going to go to graph algorithms, and we're going to see like a very cool algorithm due to Kargers and Stein actually, called randomized min cut. It's basically a way to get a very good min cut very fast. And after that, we're going to go towards probabilistic data structures, so hashing, Bloom filters, then like dimensionality reduction, LSH, locality sensitive hashing. I'm just saying words right now, but they will make sense. And if you know them already, like get excited. But after that, we're going to see something about streaming. So what if your algorithm gets the input data like one little piece at a time and can't keep all of it in memory? What can you do? Can you do anything? And after that, we're going to see linear programming's randomized rounding. So a lot of cool stuff that you can do with randomization to get good quality out of an approximation. Then embeddings, I have something that's not a tree. Can I just somehow put it in a tree, like a binary tree, or embeddings basically. I've got something that lives in a weird space with distance that I don't know really what to do with. Can I just like embed that in a nice structure and like solve the problem on that nicer structure? That's what those things are about. And we're gonna conclude with something like some correspondence between two things, one sampling and the other counting. So again, don't worry too much about those words if you don't know them already. We're gonna see them. Hopefully you're gonna like the topics. I'd like to say I'm gonna conclude here, but I'm gonna leave you with like something completely different. I promise you a bunch of tricks that can be used again and again. This is a very good one. So, you're gonna prove that in the tutorial, by the way. This is the usual definition of expectation for discrete random variables. At least if they are like non-negative. That's why I only have to start at 0 and integer value. So that's the usual definition of expectation. But this is sometimes way more useful. So this is just an identity. Like if you've never seen it, it's kind of mind-blowing the first time you use it. Sometimes it makes things way easier. It's actually not hard to prove. You're going to prove it in the tutorial. All right. So that's all for this lecture. I'll see you live in week 1, but yeah, hopefully you didn't fall asleep during this one. Feel free to watch that as like 2.5. I should have said that at the beginning. Feel free to watch that at 2.5 speed, and yeah, see you soon.